Milky Way, got it. The Milky Way is resplendent as it always is. Deneb in the north and Altair is high overhead in the northwest. Those are prominent stars, especially in the northern hemisphere, north of our ecliptic. And Saturn is prominent high in the east. That's the brightest planet in the evening. Right, at now the sky changes over time. And at midnight, Orion, Sirius, and Aldebaran are in the east. Orion has just come up. Canopus, Achernar, and Fomalhaut in the south. The great square of Pegasus is prominent. It's easily seen. Jupiter is high in the north, and Saturn is in the west, about to go down. So early in the evening, you see Saturn in the east, but by midnight, it's right over to the west, and Jupiter is high in the north. Just before dawn, Crux and the pointers are in the south, Canopus and Achernar in the southwest, whereas they were in the south, they're now in the southwest. Sirius, Orion, and Aldebaran high in the west, Regulus in the east, and Capella in the north, and Venus in the east. Venus is the bright planet you see in the morning. Those you get up, like David Slater, will see Venus early in the east. All right, next one. This is just, you've all seen this. I've just shown for interest the ecliptic and also all the zodiacal constellations. In summer, well, now we see the constellations. If you look at the bottom, there's Gemini. Then you go to Taurus, Aries, Pisces, Aquarius, Capricorn, Sagittarius, and Scorpio's in the west. So you start in the east with Gemini and go all the way to Scorpio in the west. And those are major constellations. Just for this, in winter, we have the other constellations visible. Now, I mentioned last month the top 100 deep sky objects in the southern hemisphere is drawn up by the Astronomical Society of Southern Africa, the top 100. We dealt with about 5 of them, the first 5, and what I'm going to deal with is another 5 now. These are very interesting deep sky objects which are visible by eye, but definitely with binoculars. You certainly don't need a telescope. So if you go out into the night sky, and I'm going to tell you where to look for some of these, you can pick them up with your binoculars, or if you've got good eyes, then with your naked eye. So let's just look at some of these deep sky objects. They are I find them very interesting. And they're visible now, ones I'm going to talk about. So I've mentioned 5. It's the National Global Catalog and the various numbers. What is it? So the one is a globular cluster, the next one's a nebula and tarantula nebula, and then 2 open clusters. And where to find them? First one is Tucana, north of the Small Magellanic Cloud. NGC 1977 is close to the Orion Nebula. So you have 2 nebulas close to each other. I'm sure all of you know where the Orion Nebula is. It's just below the belt. The Tarantula Nebula is in the constellation Dorado, which is in the Large Magellanic Cloud. The open cluster, the first one, 2287, that's in Canis Major. It's just below Sirius. Sirius is easy to find because it's the brightest star. And Canis Major is just below Sirius, and that open cluster is there, NGC 2287. And 2362 is also in Canis Major. Now I'm going to show you actually what these constellations, what these deep sky objects look like. So the first one is NGC 362. It's a globular cluster, and it's located in the constellation Tucana. In the bottom left-hand corner of your screen, you should see a small cutout from one of those pages. Looking south, it shows you Tucana. It shows you the Small Magellanic Cloud, and the globular cluster is just slightly north of the Small Magellanic Cloud. So then if that picture would have been taken, say, from Hubble or the James Webb camera. All right, the next one is NGC 1977, called the Running Man Nebula. And that's it's very attractive. I can't see how they get Running Man out of that, but you are probably better at it than I am. I probably lack a bit of imagination. I've shown you in the bottom left-hand corner where to find it. There's the map of Orion. You can see the belt, and it shows you there the Orion Nebula. Now, this is very close to the Orion Nebula. So find the Orion Nebula, and then you'll find NGC 1977. And that is a nebula, a place where stars are born.
Why?
Next is the Tarantula Nebula. Tarantula Nebula is at the bottom of the Large Magellanic Cloud, also looking towards the south. It's a gigantic star-forming region, a little like the Milky Way. The Milky Way is Orion Nebula, so it's similar to that, but it's a nebula. It's not a cluster. It's a nebula. At its center is a cluster of stars called R136, whose energy causes the tarantula's gases to glow with the emissions of gases, mainly hydrogen and oxygen. I need to just move this. Sorry. I want to see what I've written here. The recent James Webb Space Telescope near-infrared image has revealed thousands of stars that had never been seen before. It's very interesting. So you can see that with binoculars, easy peasy. The next one is an open cluster, NGC 2287, and that can be seen with a naked eye. If you look at that, that's in Canis Major, just below Sirius. As I said, Sirius is the brightest star. And so you look for Canis Major just below it, and then you can see this open cluster. It's a gathering of stars conveniently located in the night sky, making a desirable target for amateur and professional astronomers alike. So that's the open cluster, NGC 2287. And the next one is another open cluster, NGC 2362. And that is in Canis Major as well. It's very attractive. Can't remember the name. It's just called, it's a Canis Major cluster. It's an open cluster, group of stars born from the same molecular cloud. This means that all of the cluster's members share a common chemical composition, are loosely bound together by gravity. You can see this with binoculars. You won't be able to see this with the naked eye. But again, you need a dark night. Don't fool yourself in thinking you can go out tonight and see it. You have to wait for dark night. Preferably go to Kutsi or Mabuza-Hubi, and then you'll definitely see them. So these are my references. The first one I mentioned is that Guide to the Night Sky by Dunlop and Tyrion. Yeah, I don't know if you can see it because I haven't got my view here. Then have a look at the Webb telescope images from NASA. They're very interesting. The website of the South African Astronomical Observatory, and there's the website address, is full of interesting facts. And lastly, our Astronomical Society of Botswana doesn't need to stand back. I think it's a fabulous website. So feel free to go through it quietly at yourself. And you'll also pick up some of the previous talks that have been given and my talk tonight for reference if you need it. And that's my story. Thanks, Gian.
Thank you very much, Harold. And I wonder whether there are any questions for Harold. From the live viewers or the virtual viewers. Thank you, Harold.
Okay.
I'd like to present our main presenter. He's an advanced level student from Lekhai Academy here in Gaborone. He's Achal Gupta. And I first heard him speaking with Professor Tebi at Northwest University in Mahikeng. And Achal is a IMO Botswana representative. That's International Mathematics Olympiad Botswana representative for 2021 and 2022. He topped the country in AS level mathematics and in computer science. And his presentation today is going to be a very fascinating presentation. And over to you, Achal.
Good evening, everyone. Today, I'm going to be talking about how we have plans to unite all the physics that there is in the universe, because I'm going to talk about why we haven't been able to, how we're planning to, and some experiments to prove this theory. Before we start though, I just request that you ensure that your phones are on silent to avoid any disturbances during the presentation. Okay, so now I'm going to be talking about the between the theory of general relativity and the standard model. So this is one example. I'm going to give another example as well. In general relativity, we have this concept called time dilation, and this is that time will pass at different gravitational strengths. So if I'm standing at the surface of the Earth and an astronaut that's in no gravitational field, time will pass differently for us. Time will pass faster for me. If you just tell, I'm sure you're familiar with this concept. This has been proved experimentally as well through satellites that have eccentric orbits. So they'll approach the Earth and come really close. Then they'll go far away from it, and they can take measurements at both points and realize that time is moving at different speeds. That's what general relativity says. The standard model says something totally different. Account for gravity can bend time like that, and as a result, it will create flawed predictions. Another example is gravitational. So when we're in a really extreme environment, such as near a black hole or the gravity is really intense. And if those objects are moving really quickly, for example, if we have two black holes and they're each other, what's going to happen is they'll carry energy away from themselves, right? And that momentum will be transferred into the actual fabric of space-time. called gravitational waves. So that's effectively us bending the universe. So gravitational waves is something that's also been tested and confirmed, and it was 2015. Again, the standard model does not account for it, and also for the graviton. I'll talk about the graviton later on, but in summary, the graviton is just a particle that carries the force of gravity. Just like we have the photon that carries light, we have gravity. So move towards a solution, which we term a theory of everything, and we'll have different ideas about the theory of everything. So I'm going to start with dimensions. So we talked about how Einstein used warps and curves to describe how gravity works. So those were our 3 dimensions: up, down, left, right, and forward. Then there was another scientist, and he wanted to do the same with the electromagnetic force, another known force at the time that Einstein released his theory. And he thought that if Einstein used up these 3 spatial dimensions, what other dimensions could he? Because there's no other dimensions left. So what he predicted was that there's extra, and those dimensions are responsible for the working of the electromagnetic force. Mind you, in the 20s, we didn't know of any dimensions, extra dimensions. We still don't know of them now, but the proposal was still made. And now, because people were asked what dimensions are, in 1926, another idea cropped up that these dimensions are very hidden away from us, which means we're unable to see them and we're unable to those dimensions. Let me give you an analogy. Pretend there's a man walking on a tightrope, right? From my, I can just see one long line, so that's one dimension. For the man on the tightrope, forwards and backwards, right? There's nothing else he can do. But let's picture that there's an on the tightrope. The ants can also move forwards and backwards, but it can also move in a tiny around the circumference of the tightrope, which that while the man is only perceiving one dimension, which is forwards and backwards, the ant is perceiving 2 dimensions, which is forwards, backwards, and that little tiny curve. So that's the basic idea behind these. It's that most of these hidden dimensions are tiny, curled up dimensions within space-time. That's why we're not able to perceive them. Now I'm going to move towards the basic idea of string theory. And we're going to start with a little experiment. I'm sure we've all done this before. If we take an orange and we break it down in smaller particles, we'll eventually get a molecule, right? The molecule that makes up the orange. If we split the molecule as well, eventually we'll get the atom, right? Now, if we focus closer to the center of the atom, we'll get the nucleus. Now, the nucleus is made up of particles, and one of them is a proton. If we zoom into the proton, we get 3 quarks that make up the proton, right? And this is where conventional. Now, what string theory suggests is you can go further down from the quark. You can have this small filament, picture it as if it's a rubber band, called a string, right? And that's string theory. That's where it gets its name from. That there's particles smaller than a quark that make up the entire universe. This is where our theory of unification comes from, because if we have just strings, the entire universe, then it will account for all 4 fundamental forces. Now we're going to be talking about the properties of these strings in passing. We have 2 types of strings. We have open strings and we have closed strings. So open strings, as you can see, a loose bit of string. You can picture it as a loose bit of string that has 2 endpoints. And at these over here and here, interactions can occur so that the endpoints can connect to other open strings, can connect to things we call branes. I'll talk about that in a moment. And I'll also explain how the interactions occur later on. Then we also have closed strings. Now, closed strings have the type of interactions that open strings do because they don't have any endpoints. They're a little loop, means that they can't connect to any other open string or any other brane. Another property of strings, modes. So this is basically the frequency of vibration of the Picture me taking a loose string and tying it at the ends and then just plucking it, a violin or plucking a guitar. You'll see it you'll see it, and if I put more energy into it, it'll vibrate at a high frequency and you'll hear it. So here, higher modes of vibrations are analogous nodes and antinodes. And you can see the nodes are the points that don't move, and antinodes are the move the furthest of the equilibrium point. These modes are quantized, which means it isn't continuous. There's only a specific number of them, and they're only specific values they take. Now we move on to closed strings. Their vibrations are quite similar to open strings, except they don't, not only do they determine the particle they are, but it determines what type of gravity particle it is. Closed strings don't have the same type of interaction as open strings, and closed strings only give rise to particles associated with gravity. Similar to open strings, categorized into different harmonics with a corresponding number of nodes and antinodes. Now we move on to the topology and geometry. Open strings can have topologies. As long as you can draw two lines, as long as you can draw two endpoints, it can be a topology of an open string. You could have a perfectly straight line, have these shapes. You could have any shape that you can think of that has two endpoints. Another property is their tension and stiffness. Think of this respect to a guitar or violin. The tighter the strings, the harder it is to pluck it. And in this case, the tighter or the higher the stiffness of the strings, more energy needed to these vibrational modes. Closed strings only have one topology, circle, or that they're closed loops. They can't really form any other shape. So that's that for closed strings. Now, talking about mass and the spin of strings, this is pretty much identical for both types. So the mass of the string is determined by the energy of it, and as in the previous slide, the energy is determined by how stiff the string is. Energy, the greater the mass of the resulting particle. And for instance, if we take the force carrier, the gravitational force, it is massless and it has the lowest, which is also called the background state. It's important for the graviton to, because this means that string theory now agrees with the theory of general relativity. And obviously, because we're now quantifying what carries the gravity, it also agrees with quantum mechanics and the standard model of physics. Now, talking about the spin is a measure of the string's angular momentum, and it can take on any value. It doesn't have units. It takes on any non-negative value. So it can take on the value of 1. It can take on the value of 2, and so on. And different vibrational modes give rise to different spin values, and different spin values give rise to different particles. The graviton has a spin of 2, like we talked about. Interaction is pretty different if it's an open string or a closed string. So strings interact by exchanging these vibrational modes I was talking about. How they do this is they approach each other and they exchange vibrational excitations, and we can interpret this exchange as a force. Open strings can exchange both open and closed, and since we are saying closed strings can be gravitons, that's how we can get to the gravitational force. Open strings being exchanging gravitons, and that will lead to a gravitational force being. Similarly, the exchange of photons will mediate the electromagnetic force. This presentation is because photons coming and reflecting and you're able to see it. For closed strings, they only interact with others because they don't have endpoints. And what they can do is they can self-interact. So they can split, combine with other closed strings, and they can exchange energy and momentum amongst themselves. Obviously, they have to have the laws of conservation of energy and momentum. Now I'm going to talk about a little bit. So branes is short for membranes, and these are mental objects that exist in high dimensional space. This is just the technical definition. You don't need to. Basically, branes can be of various different types. So you can have zero, basically dots, because they have no width, they have no height, they have no length. So In traditional physics, we call these point particles, but in string theory, zero branes. Okay, moving on to one branes. These are one dimensional. So they don't have any height, they don't have any width, they only have a length. So these are strings I was talking about earlier. So open strings can attach to these one branes because one branes are also, and their motion is always confined to the brane, which means that if I have one to a one brane, they can only move on that one brane. They can't just move somewhere else. They will have to detach. So that's a sort of rule that strings. Moving on to two branes. Again, two branes, they don't have height, but they have a width and they have a length. So they're basically these flex sheets. You can picture it like paper, and they can deform, they can move around, and they can also connect to other two branes using strings or one branes. This is not where it stops. As the pattern continues, so you have 0 branes, 1 branes, 2 branes, 3 branes, 4 branes, 5 branes, 6 branes, and they'll have that many dimensions. This is an example of how two branes could be connected. The project is not showing it very well, but this is another two brane, and we have these open connecting them. See, they have two distinct endpoints, which is what I was talking about in terms. So now I'm going to talk about a special class of branes. We call it D branes. Talk about this earlier as well. And these are basically branes that impose, they're kind of law officers when it comes to string theory. They impose on open strings. Connected to a D brane. And as I mentioned with the rule of branes, when an open string time, it's confined to the brane, so it has to move and still be connected to the brane. So space-time, it's required to be attached to a D brane. This is sort of your default option. Similar to regular branes, you can have D0 branes, D1 branes, D2 branes, D3 branes, and it goes on. The presence of this specific branch of branes also lets us talk about gauge theories, which are basically all four fundamental forces. Now, I'd like to talk about experiments that will help us check validity of these theories, because string theory isn't one theory, it's a branch, and it's got many different variants, and the details, minor details, are different on which variant you look at. So one of the experiments we can do is particle colliders. There's heard of the Large Hadron Collider in Switzerland. The idea behind it, it costs $3.6 billion to. And the idea behind it is that it's going to accelerate particles to very, very high speeds. It's going to pump a lot of energy into these and collide them together. The idea is that colliding them together at a high enough speed, new particles that haven't been seen before, or new effects that haven't been observed or can't be, and then that could provide insight into whether string theory is a valid theory or not. Have the CMB, which is the cosmic microwave background. This is the afterglow of the Big Bang. It's sort of a signature that the Big Bang did exist. And by studying it further, we could also get insights into how string theory works. And we can also get a better understanding of how the universe formed. The third thing is cosmic strings. Now, these light and dense energy structures, basically collections of energy left over from the earlier forms of the universe, and indirectly observing cosmic strings may also provide evidence for string theory, because what we can do is we can look at the effect they have on the matter surrounding them, because we can't look at them directly. The hope is that we'll be able to get better insight into string theory. We can also neutrino oscillations. So neutrinos are weakly interacting particles. They don't interact with regular matter as much. Yes, if we can observe neutrinos, which is a very mind you, we can also get insights into string theory, because we can predict about these particles, then we can study these particles and see if it's right with what string theory is saying. Match some solid evidence that string theory exists. About dark matter and energy, I'm sure we all know about this. Dark matter and dark energy make % of the universe, and we still don't understand this, even though it makes up so much of our universe. So hopefully, the idea is, if we can manage to observe it with energy, we'll be also able to compare it with the predictions of string theory and some substantial evidence that it is a valid theory. Then also consistency. String was proposed in the 1920s, and from then till now, it's known for its mathematical consistency, because it's been put through a lot of scenarios, and it gives very accurate predictions that are in line with both the theory of general relativity and if we continue to look at string theory in detail, scientists continue to look at it in detail, get circumstantial evidence for its validity. I'm sure you might be asking why we're doing all, especially since I mentioned that these are very expensive projects to undertake. For example, the LHC, or the Large Hadron, $3.6 billion. So just to ask why we want the theory of everything. So firstly, speaking, the theory of general relativity and the standard model have not come together well. The boundary between them, and it's very difficult to make those theories agree with each other, as I showed you with the examples earlier. So the best would be unification. We'll have all four fundamental forces, which are gravity, electromagnetism, and the weak and strong nuclear force, united under one umbrella. This means a theory that accepts everything around us, and we won't have to rely on one theory for one scenario and another scenario. This will also help us accurately understand the behavior of matter and energy throughout the universe. Constants. There are multiple constants that define our universe. There's a list of about 20 numbers, and if those numbers have the value that they were slightly higher or slightly lower, then our universe would not have existed as it exists right now. This means that we still don't know why those constants take up the values that they do, and we hope we can get a theory of everything that will help us explain why constants such as the gravitational constant or Boltzmann's constant have the values that they do. As I already mentioned, string is the origin of the universe, and it can help us understand how a universe formed, and gaining a better understanding of how formed will help us understand the future, and it'll help us as a species survive. Black holes. Black holes is a mysterious topic, has been for a while. String theory promises to help solve fundamental questions around black holes. For example, the event horizon, which is the point, and if you cross the event horizon, you'll never come back. We don't know what goes on beyond the event horizon because, speaking, if nothing comes back from there, there's no way we can tell what goes on in there. So the idea is, we can make accurate predictions about what goes on beyond the event horizon, and maybe with the concept of dimensions, we can also get a new view or a new perspective on how black holes would work. Matter. This is a reversible role because string theory can help us understand, and dark matter can help us understand string theory. So getting insights in either one will help us greatly understand the other. So theory of everything proved through some other method, it will also shed light on dark matter, and we'll also be able to understand how 95% of our universe works. Dark matter is also responsible, or is believed to be responsible, for the expansion of the universe, and understanding dark matter would how it will expand and which theory about the future of the universe is most likely to happen. Then the extra dimensions. Since the theory suggests that there are more than 4 dimensions, trying to look at, Some will suggest that there's up to 11 dimensions. Some will suggest that there's up to 26 dimensions. But which look at, it will give us huge insight into where these dimensions are, where we can find them, size, and if there's any limitations or rules in those dimensions. It'll help us understand that as well. It will also be a problem, which is that we don't understand why gravity is so much weaker than other forces. Let me give you a little quick demonstration. Tiny magnet, two tiny magnets. You place one on the table and you hover the second one on top of the first one. The one on the table will quickly hover the magnet in your hand. What this means is the magnetic force between those two tiny pieces of metal is much stronger than the gravity of tons and tons of rock that make up this planet. So gravity is much weaker than these other forces, and we haven't had an explanation for it till now. String theory will be able to provide us insight into why gravity is so weak. Now, if we let our imagination, some indirect advantages that string theory could potentially have is that in propulsion systems, for example, right now, NASA is thinking of returning to the moon. Then on the way to return to the moon, to go to Mars. But the universe is much larger than that. We have multiple stars in our own galaxy, then we have multiple galaxies in the universe. So in the future, manage to prove string theory is a valid theory, then the radical approach that it produces, that is different from classical physics, may help inspire newer ideas that could has better propulsion systems and might even allow us to travel faster than light. Traveling faster than light effectively means we're trying the fast. Another very far-fetched thing that could happen with string theory is exotic physics. We could new branches of physics pop up because we have these new particles, new dimensions, and possibly new universes that would theory. And we could use these particles. We could harvest the energy from these particles. We could harvest the energy, or we could find more efficient ways of using energy. And that, as a species, could solve many problems we have. For example, its energy crisis would also have a solution to that. Thank you. Do we have any questions? Anyone, even online, any questions? I don't think there's any questions. Okay, yeah, there's one.
Okay, so like in the last slide, you said something about interstellar issue, right? Interstellar issue, right?
Yes.
So that means would be able to travel high because of strings, right? Because
The idea is that
can help us
new dimensions can help us
design systems that can travel faster than light. If we can travel
systems
faster than
that
light,
can help
then
us
we
travel
can
faster
reach
than light.
very,
If we
very
can travel
far
faster than light,
objects
then we can
because they're
reach
really
very, very
far
far
from us.
objects
So
like
it wouldn't
stars,
take us
because they're
that
really,
long to reach
so it wouldn't take us long to reach it.
so it is a long time for us to understand
No, gravitational waves is separate. The reason it takes long to reach the stars is because our current technology
lets us
move at a certain speed. And if we were to travel at that certain star, it would take us thousands and thousands of years to reach that. Right. So the idea is we have open strings and we have closed strings. So these connect to brains. And because the brains can have multiple, the brains exist in a high dimensional space, regardless of what dimension they have. Because they exist in that high dimensional space, and they connect to two brains, they connect to four brains, that will be able to hide a link between strings and dimensions. Yes. Yeah, that is another mystery. Yeah, that is another mystery.
How
String theory,
a
because we're
photon
not
has
sure
no mass.
how a
And
photon has
it's
no
able
mass.
to accelerate from 0 to its maximum
Able
speed
to
the moment
accelerate
it's
from
formed.
0 to its
And it
maximum
stays
speed
at that
the
maximum
moment
speed
it's
and
formed.
travels in a straight
And
line.
it stays at
We're
that
not sure
maximum
how
speed
that
and it
works.
travels in a straight line.
That is another mystery that string theory
How
could
that
answer.
works, that is another mystery.
Any other questions? Yes. Travel between stars.
Between star systems.
So string theory. So yes. String theory.
Right now, string
Theory is still
a theory. It's pushing
a
the
theory.
word.
It's pushing the
theory.
word.
So there isn't any practical example for it.
So
But
there
I
isn't
could
any
imagine
practical example.
artificial
But I could
intelligence having
artificial
applications in string
intelligence
theory
having
in the
applications
very
in
far
string
future
theory
when we
in the
actually
very
start using
when we actually start using both.
So since the string theory is a theory, mathematics.
yes.
it is.
String
String
theory
theory
is
is
strictly a
theory.
theory. That's why I was talking about the experiments that we have to prove that.
That's why I was
We
talking
still
about the
don't know
experiments that we
if
have
it
to prove that.
exists for
We
real.
still don't know
still think
if it
is a theory.
exists for real. We still think it is a theory.
So why do scientists believe that it's actually the
Because of its mathematical
Because of its
consistency.
mathematical
If you look at the
if
equations
you
that
look
string
at the
theory
equations
uses,
that string theory
it's able to
uses,
cover the theory of general relativity and the
cover
standard
the
model.
theory of general
And it's able
relativity
to
and the standard model.
produce
And it's able
results.
to
If you
produce results.
combine the equations, you're able to get results that are consistent between general relativity, the standard model, and string
You're
theory.
able to get results that are consistent between general relativity, the standard model, and string theory.
So in theory, wrong given there, run that goes to
It wouldn't be completely ruled out. It would just be
It
assuming
wouldn't
that
be completely
maybe
ruled
there's
out.
a
It
tiny
would just be
detail
assuming
in
that
string
maybe
theory
there's a
that
tiny
hasn't been
detail
tweaked,
that hasn't
to
been
make
tweaked,
it perfectly applicable
make
to
it
our world.
perfectly applicable to our.
Because there's many multiple variants. So some of them
Because there's
have
many,
certain flaws
some of
in
them
certain
do have
areas.
certain flaws.
For example, the original idea.
For example, the original idea of
was-
string
did
theory
not account for the electron.
did not
But
account for
later
the
that was
electron.
modified. And our current
most
probable
most
accurate version of string theory is
string
the
theory
M
is
theory.
the M theory.
So yes.
So if the M theory is to be correct, that means that the scientists or astrologists or something can start working on the methods to find interstellar loop, right?
Well, not immediately after that, but yes, it would be a huge scientific breakthrough.
But
If
yes,
M theory is the
is
perfect
the
theory of it.
perfect theory of it.
Is that all?
Wait a minute. There is a question online. I have read that the string theory is calculated to only apply for universes with 5 or more dimensions. So, how do we confirm that it applies to us? Are there hidden dimensions or are there calculations still needing to be done?
Okay, so again, this depends on the variant of string theory that we're talking about. If we talk about the original idea of how hidden dimensions work, the idea is that I want
to take us back to the title.
Yes. So the idea is that for the man on the title, the dimension of walking around the diameter of the string is not possible because he would fall. But for an ant, it's possible. So for the man, that dimension is hidden from him. But for the ant, that dimension is not hidden from him and he can access it. So it's this difference that it makes hidden dimensions so elusive. So we can't exactly predict how many dimensions there are. Again, the variants predict different levels of dimensions. Some say 26, some say 11, some say 5. But yeah, calculations. In terms of calculations, I'm not aware of any calculations that are pending to prove hidden dimensions. I think it's when string theory will be proven as a valid theory overall, we get more insight into that. Yes.
So as men are able to see these hidden dimensions, how is it possible to think that in future we'll be able to see them?
No, we still won't be able to see it with our natural form. The idea is we'll have machines see it for us. We can't look at electrons right now with our eyes, but we have machines that help us look at those electrons. So the idea is that a similar policy will get with strings. We have a hand raised there. We have a hand, someone raising a hand. Do we have any other questions? Okay, so I think we are done with the presentation.
Thank you very much, Achal. It was very informative. And thank you so much for all the work that you put into this presentation.
Thank you.
Thank you, everyone, for participating. Good night.